All right, so possible topics for the final exam. Let me start from the end and work towards the beginning, okay? Because the stuff in the beginning, we don't really have as much to say about it. So things you should be prepared to do. Put together code to implement a structure, okay, kind of like you did on the midterm. Do basic operations with pointers, dereference pointers, pick off fields from a structure or a pointer to a structure, right, with arrows. All those things, the basic mechanics, you're good with all that stuff. So not too much to worry about there. Analyzing code. So I may give you a snippet of code, okay, that does something and ask you some questions about it. Okay, it's not going to be 80 lines of recursive jumble, but basic behavior, right? I might ask you to modify some code. So here's some code for doing this, make some changes so that it does that. Okay, so analyze and then make some edits to it. I might ask you to write some code. Well, I'll definitely ask you to write some code. Okay, and it will generally not be 80 lines of stuff. So try to pay attention to what the question's actually asking. Okay, if it says write a program, that means integer main. If it's write a program that takes command line arguments, it's main, argc, argv, that kind of stuff. If it says write a function, you don't need a main program. Okay, if I say write a function to take two numbers and return their sum, integer function sum a comma b, etc., etc. You just run with that. That's not one of the questions on the final though. If I ask you for a few lines of code, you don't even necessarily need to write a function, right? I might say, here's a structure and write some code to, reverse the elements in the list or something. That would be a rude one. But I'm looking for a loop or a set of code or conditionals or something like that. Definitely be comfortable with recursion. Okay, we'll be working with recursive code. I may give you a recursive definition you haven't seen before and ask you to write some code that does something based on that. Okay, so as you're studying, you want to go for concepts more than particulars. The particulars are good to practice on, right? But I'm not going to say write some code to insert an element at the beginning of a linked list. Okay, you've done that. You've done it in ODPs, you've done it in programming assignments. I'm not going to ask you to write that down on paper. But I might do something that is similar to that, but that you haven't done already. So make sure you understand concepts. Performance of algorithms, not a whole lot to worry about there. We'll talk about sorts, and I'll mention algorithm performance there. Lists, trees, tries, hashes, stacks, queues, other data structures. You definitely want to understand those, and I may ask you to do some things on paper. Okay, so here's an implementation of a hash, and here's a hash function, and here's some data, and show me what happens when you try to store this in the hash. Right, so run it through the function and use the probe numbers and deal with collisions and so on and so forth. So I may have you working with some of these structures on paper. GDB, Valgrind, Makefiles, other tools. I'm not going to ask you a lot about those, if anything, okay? But you've been using these throughout the quarter, so you know what they basically do, right? So not a whole lot to worry about there. And then sorts, trees, hash operations, things like that. Again, I might give you a list of numbers and say, if you do a quick sort on this, show me the first, few steps of how this data gets rearranged for a quick sort or a merge sort or insertion sort or something like that. All right, so let's look at particular topics. So heaps, all right, basic concept of a heap. There's a heap property, and it tells how the parent's value relates to the children's values. And max heap, the parent should be largest, min heap, parent should be smallest. So know the difference between max heap and min heap, up heaping and down heaping, okay? Whichever type of heap it is, this is always the same. When you want to insert into a heap, you move your new node to that last position and you up heap. Okay, upheap basically says see if the parent satisfies the heap property, whatever that property is. If it doesn't, swap with the appropriate child and then repeat that process until you get to a point where the heap property is satisfied. So insert, put at the bottom, upheap. Deletion, remove the root, that's the extreme value. Move the last node up to the root and then down heap. Okay, so insert, upheap, delete, down heap. And it does not depend whether it's a max heap or a min heap. It's always insert, put at the bottom, go up, delete, put at the top, move down. All right, heapifying was this technique we had where you want to make a heap out of a set of data. You just throw your data in a heap-like shape. So you just fill in from top to bottom, left to right. And when you're done, now you go through this heapify process, which says start at the last node and see if the heap property is satisfied. And if not, make the adjustment and move down and see if the children satisfy the property. So lower level, there's nothing to do because there's no children. Second level, you may have one adjustment to make, right? If the heap property is not satisfied, you're going to swap with the child, and the child has no children. And so you move up like this. And the main thing to know about heapifying, other than how to do it, is that it tends towards order n, as opposed to n log n. So you can construct a heap out of data with n operations instead of n log n. And we talked about implementing heaps with an array, and this was the idea of starting your heap in memory at index 1, and then you can use this integer, this index arithmetic, to move between parents and children. And that's an efficient way to implement a heap because all you're doing is swapping parents with children, which means you're just moving two things into each other's place. You're not inserting in the middle and moving things around, or deleting and squishing them up.
Did you say Heapify was log in or n log in?
Heapify is n.
Oh, n.
Yeah.
Right.
So Heapify is looks like n log n, but if you actually work out the numbers, it's n. Whereas inserting into a heap is log n, deleting from a heap is log n. So if you wanted to insert n things into a heap, that's going to be n log n. But if you heapify, which is different from just inserting one after another, that's just order n. All right, sorting. We've got bubble sort. You've known bubble sort since birth, right? Insertion and selection sort. So those are all n squared performance. Insertion and selection, make sure you know which is which. Okay, insertion sort, you insert in the correct order. Selection sort, you select from your input list in the correct order. So in insertion sort, as you move things into the output, you're figuring out where they belong. Okay, you're kind of doing the work on the output side. Selection sort, your output's always going to be sorted. You're just sticking on to the end of the output, but you're choosing the correct thing to put into the output list. So we would select the smallest element and then select the next smallest and select the next smallest and so on. So those are all n squared. Merge sort is a divide and conquer. It's n log n if you're splitting in half. And that's basically taking two sublists, sorting them recursively with merge sort, and then interleaving them. So pull off from the beginning of each array in the right order and build your output array from that. So a heap sort is basically building a heap and then just pulling off from the root, moving the tail up and down, heaping, and doing that repeatedly.
So you say you might ask for us to do the first couple steps or a portion of the sort. Would you be expecting us to like write our own like sort or heap sorts?
I'm not going to ask you to code these, no. But I might ask you to show me what this would do.
Absolutely.
Yeah, so like if
Kind of like instructions or something like that?
no, so if I said here's an array, 2, 4, 3, 7, 6, 5, 8, and we want to use a bubble sort, largest to smallest. Yeah, I won't get weird on you. We always do smallest to largest. But I will put some more numbers on here. Okay, so I might say, show me the first pass of a bubble sort. And show me each time that anything moves in the array. Okay, so smallest to largest bubble sort, right? The idea is you compare each number to the next number, and if the next number is, I'm gonna get this backwards because I wrote it horizontally. Smallest at the top. So if this number is bigger than the number after it, we want to swap them. Okay, so first pass of a bubble sort should end up with the largest number in the bottom position. So we start off with this, we compare 2 to 4, those are in the correct order. We compare 4 to 3, those are out of order. So it's going to make a change, like that. We'll compare 4 to 7, that's in the correct order. 7 to 6 is in the wrong order. And then 7 and 5 are in the wrong order. And then 7 and 8 are in the correct order. So this is all the ways that this input array would change in that first pass of a bubble sort. All right, so I'm not going to ask you to do this for a bubble sort, but that's an example. But I'm not going to ask you to code a sort like that. All right, quick sort. Quick sort, we have those 2 pointers, right? Hopefully you work through this on your own. If not, let's work through it. But you start with a pivot, right? Rightmost element, and pair of indices, first element, last element, right before the pivot, and you move that leftmost index until you find a number bigger than the pivot. Then you move the rightmost index towards the middle until you find a number smaller than the pivot. You swap those 2 numbers and you continue this process.
So if we were doing this on the exam, would we just show the swaps? Because depending on what it was, it'd be really easy to do without knowing how quicksort works. But let me rephrase this. If you had like 1 through 10, and then you mix them up and use quicksort, you just take whatever pivot and then put in that in.
No, I would probably ask you to show me
So just
every time that you
arrows
swap.
or-
I might not ask you to draw arrows, but show me how the array changes every time that you move something. So let's.
Because if I remember right, you said you didn't have to choose a pivot to be the rightmost element, right?
No, but I would have to
So-
tell you where to choose the pivot if I was giving you a question like this.
So all you would have to do in that case is just swap any 2 numbers where it solves one, and that would technically be valid.
Not necessarily.
Maybe I'm misunderstanding how it works.
All right, so let's say we want to quick sort this, and let's say that I tell you the rightmost element is the pivot. Okay, so you've got to do some of this yourself to figure this out. So I would probably say something like, show me the set of data every time that you swap. Okay, or show me the array every time it makes any change up to the point where the pivot's in the correct spot. Okay, so you would do something like this. Okay, 20 is wrong, and 9 is wrong, so we're going to swap those 2. So the first change you're going to make would be like this. All right, and then you're going to continue. This is wrong, and that's good, that's good, that's wrong, so your next change would be this. And then that's correct, that's wrong, that's where the arrows collide. And so now you're going to swap that with the pivot, so your next change would be this. And that would be the end of that first pass. So in this case, I would expect to see at least 4 lines but I wouldn't expect you to redraw this when you move the arrows or things like that. I'm just looking for the data. And if you just do this, right, if you just move the 10 into the correct spot, that's not a correct answer. Yeah. All right, Radix Sort, same deal, right? It won't ask you to code it, but you should know this process. So start with the least significant digit and move through and pull out all the zeros, the ones, the twos, or whatever your character set is, right? So that you sort based on that least significant digit, but you do it in a way that preserves the order of things that agree on that digit. Then do the same thing for the sorted list, but sort on the second digit. Same thing for the third, and keep going until you get to the most significant digit, and when you're done, your list should be sorted. So basic performance, merge sort, heap sort, quick sort, these are n log n. Radix sort has a weird calculation, right? It's order n to go through each pass, but it's order n times the number of symbols per digit, and you have to do a total of d passes, where d is the maximum number of digits in the things or characters in the things that you're sorting. So it's arguably order n, but that can be deceptive. Implementation issues, yeah. So.
Quick sort can end up being this way too.
Say what?
Quick sort.
Quicksort can end up, so we've usually been talking about typical performance when we talk about order of complexity. Again, in a more, in a longer, deeper course, you would look at average case, worst case, best case performance and things that affect those. Bubble sort, if you coded really, really nicely, it might be order 1 on a sorted list, right? Because the first time you go through, you don't swap anything. If you note that, you would short circuit your outer loop and you'd say, okay, we're done. And one pass through the data, so I guess that's order n. One pass through the data and you'd be done. So best case n, worst case n squared. But we've mostly just been talking about sort of typical case, just to kind of do a general first order comparison. Merge sort's usually better than bubble sort, that kind of thing. Dynamic programming, so you know all about dynamic programming now, right? Because this is PA5. So basic theme is we're taking a problem and we're expressing its solution in terms of solutions of smaller versions of the problem, right? So how do we find max val of 20? Well, we have to find max val of 17 and 15 and 4 and 3. And if you tell me what those are, I can put those together and tell you what max val of 20 is. Okay, it's recursion at its finest. It's how we do Fibonacci numbers. It's how we can do towers of Hanoi, egg dropping, rod cutting, minimal subarrays, maximal subarrays, all that kind of stuff, right? So you've been beating this to death, hopefully. Implementation is recursive, but a key part of this is caching results, right? Because typically in these problems, you're going to end up computing these subproblems again and again and again. Right, to find max val of 20, to find max val of 19, both might need me to calculate max val of 5. So the first time you calculate it, you cache it in memory. The next time you're asked to calculate it, you check your memory and you just read from there. So it's a speed up mechanism. All right, tries are these funky, really wide noded trees that typically we have a node for, say, each character of whatever we're trying to store. So they kind of look like this. If we're storing letters, so we have a node for each letter, and then we have this end of word flag at the end, which tells us if we've reached this point, we've got a word that's stored in our structure. So if we want to store cat, all of these things are null initially. We would have the C point to another node. And in this case, the A node would point to another node. And then the T would point to another node, which has this end of word flag set. So you got a C followed by an A, followed by a T, followed by the end of the word. Cat's part of the try. And if you want to add cab, then we have C, A, we bring this B down, and we point to another node. and there's an end of word, so we've got a cab.
Couldn't you have that be also point to the same piece line too, though? Because they both have the end of words.
You could, but then if you wanted to store cabs, right? Right. So if we want to store cabs, we need to come off the S node, right? And if we're up here, then that would look like CATS. So your cabs become cats.
So if we didn't want cats in the vocabulary, then we would have to do it that way.
Yeah. Well, you don't know what you're going to want ahead of time, right? So yeah, point to a new node and set the end of word. And then if you want to store something like CA, right, here's your C, here's your A, we can change this to a 1. And now we've got CA in our try. So I'd like you to understand this basic behavior, okay, or if I give you a picture of a try, you can tell me what words belong to that. Or you could add a word to it by drawing a pointer and putting a new node in and so on. I will not ask you to delete from a try. Okay, we didn't really go into deletion. Deletion is a little weird.
Do we need to know who invented it?
Edward Franken, I believe. No, you don't need to know that. But if you want to kill a weekend, do some Googling on Franken. Sorry, Fredkin, not Franken. Do some Googling on Fredkin and look at Fredkin Gates. It's a cool computer science aspect. He was a Watson fellow at IBM, and he was dabbling in reversible computing that generates no heat due to information destruction. And it's an interesting nanocomputing concern. But no, you don't need to know that. So basic structure of performance, right? To insert a word takes you basically however many letters are in the word, that many steps. And to search for a word, however many letters are in the word, worst case, that many steps. So very, very time efficient, but very memory intensive, because you got these big nodes and you got a new node for each letter of your word. And deletion can be a little weird. You have to do more work to delete if you want to reclaim memory. I think that's all you need to know about tries. And I am seriously thinking of coding them in 223. So that'll be good. All right, trees, on the other hand, you want to know lots of things about trees, right? And you've done this in a PA. So this is mostly second nature. So binary search trees, right? Basic property, everything on one side is typically less than, everything on the other side is typically greater than. Bless you. Trees don't have to have just 2 nodes, okay? But binary trees have 2 children, maximum. And a binary search tree has this property, everything on one side versus the other, same relation to the root. So depth of a node remember, depth is the number of edges from the root. So if we look at this node right here, from the root we go 1, 2, 3, 4 edges. That has a depth of 4. And everything on that level will have the same depth. The root has depth of 0, because you don't have to travel any edges to get from the root to the root. Okay, the height is just the maximum depth. So the height of this tree is 4. All right, the height of a tree containing just a root is easy. The depth of the root is 0. That's the only node. The height of this tree is also 0. The slightly odd case is when your tree is null, has no nodes. We can't use this definition because there are no nodes to consider the depth of, right? But this is a degenerate case. We set the height to -1. Yeah?
So there's no definition of depth for no tree.
Depth is a property of a node,
Okay.
right? So since there's no nodes to talk about the depth of. That's poorly phrased. There's no nodes for which we can talk about their depth. So that's why the height comes out with a different notion from just the maximum height of a node. All right, what else about trees? Depth, height, balance. So, someone give me the definition of a balanced tree. Someone give me one property of a balanced tree.
It's and any subtrees are also balanced.
Okay, any subtrees are also balanced. In particular, the left and right subtree are both balanced. What's another property?
They're within one height.
The height of the left and right subtrees have to be within 1. Okay? Or there's another case where a tree can be balanced.
When there are one or none.
Yeah, in particular when there's no nodes. So if it's null. If it's 1, we can apply the definition that we just heard and that'll work fine. But if it's null, there is no left or right subtree, so we can't use that definition. But we'll just say a null tree is balanced. So that's the base case in your recursive algorithm usually. All right, traversal. We have 3 depth first traversal orders that we talked about. Node left node right, left right node, pre-order, in order, post order. And the names basically tell you how to do the recursion. They're inherently recursive. So node left right, you print out the node, and then you traverse the left subtree, and then you traverse the right subtree. Left node right, traverse the left subtree, print the root node, traverse the right subtree. Left right node, traverse the left subtree, traverse the right subtree, print the root node. Right, that's all there is to depth first traversal. Breadth first traversal is queue-based, and you hammered that out in your PA, and we talked about it. And it gives you a traversal where you go across each level before you move down to deeper nodes. All right, searching and inserting and deleting. I can stick with this tree. It's a fine tree. So, inserting into a tree, there's 2 ways to do it. You can do this iteratively, you can do it recursively. If you want to iterate, right, we've got values up here. If you want to insert a node, like 27, start at the root. If you're bigger than the root, move to the right. We're smaller than the root, move to the left. We're smaller, move to the left. We're smaller, move to the right. We're bigger, move to the right. When you get to a place where that's null, that's where you add your new piece of data. Okay, that can be done in a while loop, no recursive call. The recursive version is simply, if our tree is empty, just return our node. Right? Go from an empty tree to a tree containing a root. Otherwise, if we're inserting to the right of this, insert into this subtree, and then have 20 point to that new subtree that we've inserted into. And eventually, this right subtree will look like this. It will include the 27. And then we have 20 point to that on the right. And same thing on the left. So that's just pure recursion. Okay, searching, same idea. If you want to search for something, if it's equal to the root, you're done, you found it. If not, you can move to the right or the left, depending on how it compares to the root, and then keep iterating over that, right? So if it's equal to the root, you're done. Otherwise, move left or right, and so on. So that's a while loop. You can do it recursively. If your value is equal to the root, it's found. Otherwise, search either the right subtree or the left subtree. So if we're searching for 27, it's not equal to the root. It's got to be in this subtree if it's anywhere. So call search on this smaller tree. If it finds it, then it's in the original tree. If it doesn't find it, it's not in this subtree. It cannot be in the original tree because it had to be to the right of the root. Okay, so straight recursion. All right, deletion. And I'll tell you how to do this if I ask you on a test, but we're going to stick with the algorithm we've been using. When you want to delete the root of a tree, replace it with the largest node in the left subtree. Okay, I could switch it up on you at the last minute, but I probably won't do that. So if we wanted to delete the 100, and let me throw some extra things on here to make it interesting. All right, so if I want to delete the 100, I'm going to have to find the largest node in the left subtree, right? That's this node here, 60. That's going to become the root. And then everything to the left of 60 is going to get adopted by 60's parent. Okay, but but the way this actually happens is this link changes to pick up the 55, and 60's left child picks up the 20, and 60's right child now picks up the 120, and then the root gets freed. Okay, so that's what your links actually end up looking like. What a mess. All right.
At least the computer gets it.
The computer gets it, yeah. That's why we have computers. So I will not ask you to code a delete routine. Yay. But I want you to understand how to do this, okay? And I may ask you to write snippets of code that reflect that. And if you're not deleting the root, this is recursive, right? If you're deleting something that's smaller than the root, just call delete on your left subtree. Whatever that returns, have your root pointed out on the left.
So for all the stuff about the binary search trees, if we're going to write code about it, do you want it to be recursive then? Or
I'll tell you.
Okay.
Yeah. All right, hashes. We talked about hashes. So you have a hash function, and you have keys that you're trying to store in your hash. Your hash is an array. And you're either storing keys or you're storing data associated with the keys. But the whole point to a hash is figuring out where to store your information in an array. And your hash function is what does that. It takes a key, it gives you an index in your array. And you run into problems if your hash function says, store my data right here, but there's already something there. Okay, so you have a collision. And there's different ways to deal with that. So chaining, did I put chaining first? I put probing, deletion, deleted flag. Oh well, I'll mention chaining. Chaining is basically each entry in the hash is a linked list. And you just tack your new piece of data on the end of the list. So it doesn't matter if you've got 5 things that are already hashed to this location, you can add a 6th one also, just put it on the end of the list. Gets less and less efficient because you have to follow this linked list now. So the other option is to use probing. And with probing, you have a hash function with 2 arguments. First argument is the key, second argument is the probe. Okay, and you try probing with typically a probe of 0. And if that gives you a collision, you rehash with a probe of 1. If that gives you a collision, you rehash with a probe of 2, and so on. You keep going until you either find a place to store your data or you run out of places to try, in which case the hash table is full. And then deletion, the main thing to know there is that when you delete a node, you can't just mark that entry in the array as no longer in use. Because if something else was stored somewhere else because of a collision, and you delete that node, you've got to know there was something there. So that when you try to search for this other thing, you know that once you hash here, yeah, nothing's in use there, but we had a collision before possibly, so we want to rehash. So that got us into the deleted flag. All right, queues and stacks. So I want you to know how to operate these things. You should be able to work with code for these because you coded both of them up using linked lists. So stacks are last in, first out. Okay, the last thing that you push onto the stack is the first thing you pop off. Queues are first in, first out, or last in, last out. So you've got a bunch of stuff in your queue, you put something new in the tail, you're not going to see that again until everything that's already in the queue gets removed. Okay, stacks, you could have a million things in your stack, you push one thing on. If you say pop right now, you're going to see that thing you just pushed. Okay, so the last thing you pushed on is the first thing you popped. So fundamentally different behaviors, so make sure you're clear on those. We can implement these with linked lists, you did that. We can implement these things with arrays. Okay, and I gave you some code on the midterm that implemented a stack with an array and asked you to work with it. Queues, when we implement with an array, we need a circular array. So when you get to the end of your array, you might be able to wrap back around to the beginning. And that just makes things a little different. Recursion, recursive algorithms, programming, implementing recursive algorithms. Everything we've done in here has been recursive pretty much, right? So you should be fine with that. Abstract data types. So I want you to keep in mind the idea of an ADT. Okay, when we implement a hash, we might be using probing to handle collisions. We might be using chaining, where we have a linked list in each entry. We might have a big array. We might have a small array. We might have a simple hash function. We might have a very complex hash function. None of that matters to the user at some level, though. When you're writing a program that's using a hash, all you're doing is, initialize a hash, store a piece of data, retrieve a piece of data, or maybe do some kind of traversal to show me everything that's in the hash. That's pretty much it. Maybe tell me if the hash is full. Your main program doesn't care about chaining and probing and collisions and deleted flags and all that kind of stuff. Okay, so as an abstract data type, a hash is this way of storing data that you can store and retrieve based on a key, and that's pretty much it. The implementation details, that's the chaining, the delete flag, the array, the hash function, the probes, all of that. So all the functions we've been talking about we can think of as an abstract data type. Okay, stack, first in, last out, queue, first in, first out, and so on. So just be aware of that distinction. Makefiles, GDB, malloc free, valgrind, right? I'm not going to ask you a lot, if anything, about these. You've been using these, so you should be familiar with them. And it looks like people are fine with those. Malloc, right? You obviously want to be able to use malloc in code, because pretty much any code I ask you to write, you're probably going to be creating nodes. So make sure you're comfortable with malloc. Make sure you're comfortable with size of, right? So my suggested rule for staying out of trouble, don't use size of on variables. Use size of on variable types. Okay, you can say size of struct node. You can say 100 times size of struct node if you want space for 100 struct nodes. But if you declare an array of struct nodes, right, I would avoid saying size of parentheses my array. Okay. Sometimes it'll work, but sometimes it doesn't. It depends on how you've defined it, how you've declared it. So size of, try to stick to types of variables. Pass by value versus reference, we've been talking about this throughout, right? Basically everything's passed by value. So if you want to be able to change a variable, you need to pass its address. So that's the whole ampersand and star thing. And then we're getting back to the very beginning of all of this, which is mostly second nature at this point, I believe. So stars, ampersands for pointing to and address of, period for pulling a field off a structure, arrow for pulling a field off something pointed to. Okay, so the arrow notation, find the thing this is pointing to, pull off a field. And then linked lists, we started with, we did 2 PAs on them. So sentinel nodes, searching, traversing, inserting, deleting, you know these algorithms by now, right? So be comfortable with how those things work. If you haven't done a linked list in a while, make sure you go back and review it, because it was 10 weeks ago in some cases. Doubly linked list is just having back pointers as well as forward pointers. So when we do things like delete or insert, we don't have to keep a pair of pointers, so that when we've gone too far, we know the node before. If we have a doubly linked list, we've gone too far, we just follow the back pointer, find the previous node, and then put our new node in between. And we motivated all of this sort of by looking at order of complexity of things that we do on arrays. If you insert in the middle of a sorted array, you got to move everything down so you have space, because the nth element has to go at this particular location relative to the beginning of the array. With a linked list, we break that. We can have an element between this and this that might not be right here, it might be way over there. So we don't have to move things to put something in between elements. So that's the whole lead-in to having pointers pointing to other nodes. And then structures, right? Making a struct statement, referencing fields, allocating memory for structures, all that stuff. And you wouldn't be here if you weren't comfortable doing that. That's pretty much it.
Oh, that's all?
That's all. It's more stuff than you realize probably, because a lot of this is probably ingrained at this point. And the stuff we did in the first few weeks might be getting to be second nature by now. So it's a lot of stuff, but I think you're all in good shape for this. So I won't know until Sunday night if I'm going to be here Monday, but Scott will be here, if not me. Yeah.
So it is okay for students in this class to take the exam Monday then?
Yeah, so I don't know how many of them I'm going to print up, but I'll try to print up enough for some extra students to come in, and if there's more students than I printed, then I'll let people on Monday take the Wednesday exam also. So I'm going to ask you, if you do the Monday exam, don't talk to anybody about the exam, right, in case you get the Wednesday exam. So don't talk to anybody about the exam until after exams are over, basically, okay? Unless you just want to make things up and scare people. Can you believe he had his code as such and such?
Or you could just swap the labels. Label the Monday one is Wednesday and the Wednesday one is Monday.
I could, but then if I had overflow, then I'd still have people getting the Mondays. Or I could make 55 different exams. That would solve it.
Custom exam.
Cool, all right. Well, same as yesterday's class. I'll let you out 3 minutes early. So tomorrow, come in if you, so drop off your signature sheets if you have them. Come in tomorrow if you want to talk about PA5 or other stuff. Thank you. And you have 215 homework? Okay, cool. Save me. Yeah. You always stay here. No, I'll just follow it.
Steven, you still play trumpet?
Actually,
Alright.
no. I was a percussionist. I played the only number of years.
I'm heading to my office if you want to work in there.
Yeah, I came up one time.
Oh, you did, yeah. I should talk to me. Remember that.
Nick, why haven't you made YouTube videos on your, in the Bible?
Oh God, no. We don't need to go there. I do have some really obscure YouTube videos out there though that people don't find.